Today, I'll be talking about refrigerators and physical chemistry. So, clearly, refrigerators are commonplace today, but they've undergone a great evolution from their historical antecedent to reach where they are now. In early times, the only thing used to keep food cold was ice, as shown in this picture. Then, beginning in 1755, refrigeration machines started to be designed, like this very first design by William Cullen, shown here. Throughout time, these designs have improved, reaching more modern standards like this one, and eventually becoming what we know today, this version to look like. So, clearly, refrigerators keep food and drinks cold. But why is that so important? Well, the low temperatures of a refrigerator slow down bacteria, which means food stays fresh longer. This has a lot of different effects, meaning we don't have to grocery shop as often, and we can eat fruit and vegetables that are out of season in our area. But one of the greatest effects of this is that food waste is greatly reduced. So, how do refrigerators actually work? Well, they need to use physical chemistry to operate. Specifically, chemical thermodynamics are very important in the operation of refrigerators, especially vapor compression refrigerators. The vapor compression cycle is shown below. This cycle utilizes 4 segments to transfer the refrigerant through physical states with the ultimate goal of lowering the refrigerator temp. The first law of thermodynamics is especially important when manipulating physical parameters. First law of thermodynamics is shown here. It says delta U equals Q plus W. Delta U is the change in internal energy. Q is heat. Q is positive when heat is absorbed from the surroundings into the system, and Q is negative when the system releases heat into the surroundings. W is work, which is positive when work is done on the system by the surroundings, and negative when work is performed by the system itself. So the vapor compression cycle starts at number 1 in the compressor. The compressor, as its name implies, decreases the volume of the gas through a compression process. This decrease in gas is very important. Work measures a force acting over a distance, but one of the most common ways to represent work in physical chemistry is W equals negative PdV. Or in other words, work equals the negative pressure times change in volume. Well, change in volume here is negative, so work in general is positive. Positive work represents work being done on the system, meaning external work needs to be brought in. This is usually in the form of an electrical energy source. This is why refrigerators have to be plugged into work. Now, this process is also adiabatic. So this compression of the gas occurs without any heat being transferred from the compressor system to its surroundings. So Q is 0 in this stage. Because Q is 0, we can write delta U equals just W. This process also affects entropy and enthalpy. Entropy measures the disorder and randomness of a system. The more unorganized a system is, the more free it is to move however it wants, the more entropy it has. The change in entropy is represented by this equation, ds equals 1 over T times du plus P over T times dV. Because work is negative PdV, positive PdV is equal to negative work. And because Q is 0 in this process, du equals W. Therefore, we can substitute these relationships into the original equation and get ds equals W over T minus W over T, which is simply 0. This means entropy is constant during this process. However, on the other hand, enthalpy does change. Enthalpy represents the total heat content of a system. The change in enthalpy is represented by dH equals T ds plus V dP. During this process, the work done on the compression system causes the temperature to rise, which means the molecules of the refrigerant molecules are going to be moving faster than before. This, coupled with the decreased volume these molecules can occupy, causes the pressure of the system to increase, because these molecules will be exerting more force onto the walls of the container. So, because pressure increases and entropy stays constant, we know that enthalpy is also going to increase, because dH will be greater than 0. After this compression process is completed, the hot compressed gaseous refrigerant is going to enter the condenser, where it cools at a constant pressure. This cooling releases a lot of heat into the surroundings, so much so that it can make the refrigerator feel warm to touch, and also it will make the internal energy decrease overall. When the temperature of the gas reaches its condensation point, the temperature where a gas turns into a liquid, the temperature is going to become constant. It will stay the same throughout the whole time the gas is converted into a liquid. This cooling and condensation of the refrigerant is going to cause its volume to decrease, which in turn causes work to be positive, work to have to be put into the system. Releasing heat and decreasing volume is also going to cause entropy to decrease. Because internal energy is decreasing and volume is decreasing, the entropy of the system will also decrease. In turn, the enthalpy of the system will decrease because of the decreasing entropy and the constant pressure of this process. Once the condensation process completes, the liquid refrigerant will enter the expansion device, where it expands, clearly, by converting heat to work. The expansion is going to require the system to perform work on itself. This work occurs by converting heat into work, meaning internal energy is going to increase. This is also a Joule-Thomson expansion, meaning the process occurs at constant enthalpy. Because dH equals 0, we can say TdS equals negative V dP. Meanwhile, entropy will increase because volume and internal energy increase, causing ds to be positive. Because entropy increases, pressure must decrease to make this equation true. Because ds increases, the left side of this equation will be positive. In order for the right side to be positive, dP must be negative. So pressure decreases during this process. This expansion process is also a cooling process, where the refrigerant is cooled to the temperature needed for the next compartment. Auto-refrigeration may also occur during this process. Some of the refrigerant may unintentionally flash evaporate as it cools, causing the rapid chilling of the remaining liquid refrigerant. What does this really mean? Well, just that the refrigerant will be partially liquid and partially gas when it leaves the expansion device. The refrigerant will then finally enter the evaporator, where the real work of a refrigerator occurs by absorbing heat from within the refrigerator compartment. In the evaporator, the refrigerant vaporizes and expands, meaning the system is performing work. This work is powered by the absorbed heat from the refrigerator, meaning Q will be positive and W will be negative, meaning delta U will be zero. In other words, the internal energy of the refrigerant will not change because the work being performed is using the heat absorbed from the refrigerator. This process is also isobaric and isothermal, meaning pressure and temperature do not change during it. This is necessary to recreate the physical state of the refrigerant before it enters the compressor. Because liquid is converted to gas, the refrigerant is becoming more disordered, more free to move as it wants, which represents an increase in entropy. This is also proven by the equation because dV will be greater than zero and du will be zero, meaning ds will also be zero, representing an increase in entropy during this process. This increase in entropy, coupled with the constant pressure of this process, will cause dH to be positive, meaning the enthalpy increases during this process. This completes the vapor compression cycle. Overall, physical chemistry and thermodynamics are very important in the operation of a vapor compression refrigerator. So, although refrigerators are very efficient and have undergone great development throughout their history, they're still evolving to be safer. Specifically, the refrigerants currently in use cause some environmental concerns, meaning refrigerators are probably going to evolve to function without the vapor compression cycle, which requires these unsafe refrigerants. Solid-state cooling is likely the next step in this evolution process. Specifically, magnetocaloric cooling has great potential to operate in a refrigerator. This technique alters a material's heat capacity by changing the alignment of its atoms. By applying a magnetic field, as shown in the left of this figure, the atoms of a material become aligned, causing heat to be released from the material. Removing that magnetic field causes the atoms to unalign, which allows the material to absorb heat from its surroundings. By cycling between these two, having the magnetic field on and the magnetic field off, a cycle similar to the vapor compression refrigeration cycle can be created in order to lower the temperature of a refrigerator compartment. Clearly, this is another great application of physical chemistry in the future of refrigerators. Clearly, physical chemistry is essential to refrigeration and everyday life. Thank you.